These are examples for section 6.4, rhombuses, rectangles, and squares. Before starting on these problems, make sure that you reviewed all the definitions of rhombus, rectangle, and square and how they fit in with the parallelogram, and all the properties of rhombuses, rectangles, and squares that came from theorems. Also, since all of these are parallelograms from 6.2, you also need to know those properties for parallelograms. Example 1. What are the measures of the numbered angles in rhombus ABCD? Again, all rhombuses are parallelograms, so this is not only a rhombus, but it's a parallelogram. Opposite sides are parallel. And by definition, a rhombus, all four sides are congruent. So we're going to start with angle 1. Angle 1 right here is one of the angles created by the two diagonals. In any rhombus, according to your notes, there's a property that says the diagonals of a rhombus are perpendicular to each other. So the measure of angle 1 must be 90 degrees. And then we would write by the property, or we would say diagonals of rhombus are perpendicular. 90 degrees. Then moving on to angle 2. Angle 2 is an angle that is created by one of the diagonals and one of the sides right here. Notice that since this is a parallelogram, this pair of opposite sides are parallel in addition to the other two. But if we extend these two, and then we use the diagonal that's adjacent to angle 2 and extend it, notice from long ago we have two parallel lines cut by a transversal. And angle 2 and this angle right here are alternate interior angles. Alternate interior angles of parallel lines are congruent. So the measure of angle 2 must equal 58 degrees by the alternate interior angles theorem. Then moving on to 3. 3 is adjacent to angle 2. Notice that there is a diagonal that is that's in common with both these two angles. In any rhombus, diagonals bisect each pair of angles. So this angle is congruent to this one's angle congruent to this one, these two are congruent, and those two are congruent. So this diagonal right here bisects this angle, this big angle right here, into two congruent angles. So the measure of angle 3 must also equal 58 degrees. And that's by the property that diagonals of a rhombus bisect pairs of angles. So this is 58 degrees. And then finally moving on to angle 4, notice that now that we have angles 1 and 3, we've got this triangle right here. It's a right triangle, so we can use the triangle angle sum theorem, or because it's a right triangle, we can use the triangle angle sum corollary, which simply states that you add the two acute angles and you get 90 degrees. So that's what I'm going to do. I'm going to say the measure of angle 4 plus the measure of angle 1, the measure of angle 3, which is 58 degrees, must equal 90 degrees. Subtracting the measure of the 58 degree angle from both sides, we get the measure of angle 4 is equal to 32 degrees. And that is because of the triangle angle sum corollary. Example 2. In rectangle RSBF, SF is 2x plus 15, and RB, the length of it, is 5x minus 12. SF, this entire diagonal here, is 2x plus 15, and RB, the entire other diagonal, is also, the diagonal is 5x minus 12. What is the length of the diagonal? So the relationship between two diagonals in a rectangle, remember a rectangle is a parallelogram with all four congruent right angles and opposite sides are congruent. That means this is a parallelogram also. But the diagonals being congruent is what we're interested in. And they are because since diagonals of a rectangle are congruent, we can state that SF is congruent to RB, and since their segments are congruent, their lengths are equal. So the length of SF is equal to the length of RB. And substituting in the values for SF and RB, we have SF is 2x plus 15, and that's equal to RB, which is 5x minus 12. Solving for x, we subtract 2x from both sides, and we get 15 equals 3x minus 12. Adding 12 to both sides, then we get 27 equals 3x. Divide both sides by 3, and x is 9. Taking that 9, we need to find the length of each diagonal. Starting with SF. SF, what's given to us, is 2x plus 15. Substituting in x, we have 2 times 9 plus 15, which is 18 plus 15. So SF, the length of that diagonal, is 33. And to check RB, should be the same length because diagonals in a rectangle should be congruent, as we said. So to check it out, we use that expression, 5x minus 12. Substituting in x is 9. 5 times 9 minus 12 is 45 minus 12. And we do get 33 for RB. So there, the two diagonals, SF and RB, are 33. X was 9. Example 3. For what value of x is parallelogram ABCD a rhombus? In other words, what value of x does x have to be so that these two angles are a certain amount of degrees so that this is definitely a rhombus? Remember, in a parallelogram, opposite sides are parallel. And every rhombus is a parallelogram. In a rhombus, all four sides are congruent. But also in a rhombus, each diagonal bisects the interior angles. So whether or not we have diagonal AC or not, we do have this diagonal BD. And it bisects this angle B, or angle ABC, and it bisects angle ADC. So, by the property that states that diagonals of a rhombus bisect each pair of angles we can now state that the measure of angle ABD, or angle ABD, is congruent to angle DBC. Since the angles are congruent, the measures of those angles are equal. So the measure of angle ABD is equal to the measure of angle DBC. The measure of angle ABD they give us is 6x minus 2 degrees. We set that equal to the measure of angle DBC, which they give us is 4x plus 8 degrees. Dropping the parentheses and degrees, subtract 4x from both sides, and we get 2x minus 2 equals 8. Then when we add 2 to both sides, 2 goes away over here, and we get 2x equals 10. Dividing both sides by 2, x is 5. Now taking that 5, we could find the length of BD, the measure of these two angles. They didn't ask for it, so we're done right here. Example 4. Complete the Venn diagram using the categories parallelograms, squares, rectangles, quadrilaterals, and rhombuses. In any Venn diagram, there's usually always at least 2, sometimes 3 interlocking circles or sets. And a lot of times this outer rectangle is used, and sometimes it's not used, but it's called the universe. Everything inside is called the universe. Everything out here would be outside the universe. So if we take a look, we've got everything that is consisted inside the universe. Then we have a big group here, and then 2 groups that intersect. So if we start off with our most general type of polygon here, that would be the quadrilateral. So let's use our universe as all quadrilaterals. Then within quadrilaterals, the next most general one we have out of the ones we've got here is the parallelogram. So it would be this large ellipse here, oval shaped. Within parallelograms, we either are going to have squares, rectangles, or rhombuses. Recall that rhombuses and rectangles both contain squares, so the square would be our intersecting of the 2 sets. So if we have rhombuses here in this set, and we have rectangles over here in this set, where they overlap are squares. Every square is a rhombus. Every square is a rectangle. But there are rhombuses and rectangles that are not squares. Those would belong in here and in here. Then there are parallelograms that are neither rhombuses, squares, or rectangles, and they would belong in this area here. Then, of course, we have quadrilaterals that aren't parallelograms, like the kite, the deltoid, the trapezoid that would go in here. For the next example, you will need a straight edge of some kind. Example 5. Rectangle DEFG is shown on the coordinate grid below. Find the length of diagonal DF to the nearest 10th place. In coordinate geometry, all the properties and theorems for quadrilaterals, specifically parallelograms and the ones we're studying today, also apply on the coordinate plane. So here we have rectangle DEFG, and they want us to find the length, or something very close to the length, for diagonal DF. So take your straight edge and draw diagonal DF. Remember, square, all right angles. And notice we have created 2 right triangles. Take one of those right triangles, triangle DGF, or you can take the other one. But take one of them and determine the length of the horizontal and vertical sides, DG and GF. Now, if these weren't vertical and horizontal, we would have to use the distance formula to find them. So we were fortunate enough to have a rectangle that used horizontal vertical sides. DG, we use the ruler postulate from long ago, where we take the coordinate here and the coordinate here, we subtract, take the absolute value, or simply count the spaces. Starting with D, count the spaces in between. 1, 2, 3, 4, 5, 6, 7, 8 units long. So DG is 8. GF, right here in the right triangle, would be 1, 2, 3 units long. To find the length of the diagonal, then we use Pythagorean theorem. So by the Pythagorean theorem, we have df squared equals dg squared plus the other leg, gf squared. df is what we're looking for, so df squared is equal to dg, which is 8 squared, plus gf, which is 3 squared. So now we have df squared is equal to 8 squared, or 64, plus 3 squared, or 9, and we get df squared is equal to 73. Get rid of the square on the df. We just want to know the length of df, not df squared. So we take the square root. We have to take it on both sides. Now we have df is equal to the square root of 73. They asked for us to approximate that to the nearest tenths place. So take your calculator and calculate the square root of 73. And df is approximately 8.5 units long, rounding to the nearest tenths. This diagonal is 8.5 units long. That means GE, that diagonal, is also 8.5 units long, because in a rectangle the diagonals are congruent. Example 6. A rectangle is drawn and named rectangle JKLM. Right here. Verify that it is a rectangle by using its diagonals. So, a rectangle has all right angles. It is a parallelogram, specific type, and the diagonals of a rectangle, since that's what we're trying to verify, if we can somehow connect those two diagonals together, we can make some kind of mathematical statement about them. We do know that diagonals in a rectangle are congruent. We also know, since this is a parallelogram, that diagonals bisect each other, but we don't need that one. So go ahead and draw a diagonal JL, or LJ, and draw the other diagonal MK, or KM. We know by geometry that these two diagonals are congruent. So by property that states that diagonals should be congruent, we can assume LJ is congruent to segment or diagonal KM. Well, if the segments or diagonals are congruent, their lengths must be equal. We're trying to verify this, so actually we're going to check to see if this is really true. Well, we can't use the ruler postulate here and just add units, because these are not vertical or horizontal segments. So we're going to have to use the distance formula. So recall the distance formula is the square root of x2 minus x1 quantity squared minus y2 minus y1 quantity squared. So we use this for both LJ and KM, and we write it in one equation with LJ over on this left side and KM over on the right side, finding the distance of both of them. So I need my ordered pairs. We have J at 1, negative 3. We have K at negative 4, negative 2. We have L at negative 2, 8. And we have M at 3, 7. Now that we have all the vertices ordered pairs, we look at LJ or JL first. There's J, there's L. I'm going to let L or J be my second point. So this would be Y2 here. So we have Y2 minus Y1, and then we're going to have to do X2 minus X1. We'll start with x2. So 1 minus negative 2, quantity squared, plus, now over to the y's, y2 minus y1 would be negative 3 minus 8 squared. Then coming over to km, the other diagonal, and its two endpoints, here and here, I'm going to let m be my second point this time, so there's x2, y2. Starting with x2, that's 3 minus negative 4 squared, plus back over to 7 minus negative 2 squared. This is the plug-in step. Now to start solving, we solve on the left, we solve on the right, and see if the left and right side of the equation, or is it actually an equation? Does it work? So here we go. We have 1 minus negative 2, which is 1 plus 2, which is 3 squared, plus negative 3 minus 8 is negative 11 squared, equals the square root of 3 minus negative 4 is 3 plus 4, which is 7 squared, plus 7 minus negative 2 is 7 plus 2, which is 9 squared. So then at this point we come back over to the left. We have the square root of 3 squared plus negative 11 squared. 3 squared, keep your square root, is 9 plus negative 11 squared is 121 equals the square root of 7 squared is 49 plus 9 squared is 81. Then coming back over here to the left, we have 9 plus 121, the square root of 130. Over on the right side, we have the square root of 49 plus 81, which is also 130. Now that we show that the left side equals the right side, we have verified that LJ and KM are indeed equal in length, therefore they're congruent, and because they're congruent, this is a rectangle. We've verified that it is. So let's finish up by saying, therefore, LJ, or JL, is congruent to KM, and JKLM is a rectangle. Example 7. Determine whether parallelogram MNPQ is a rhombus by its definition. So they're specifically telling us to use the definition of rhombus. The definition of rhombus. We have a parallelogram in which all four sides must be congruent. Definition of rhombus. So by using that, the part of the definition that's specific to the rhombus is that all four sides are congruent to each other. So we're going to have to show that the length of LNP is equal to the length of PQ, which is equal to the length of QM, which is equal to the length of MN. Now before we get ready to do the distance formula 4 times, notice that 2 of these are horizontal. So we kind of lucked out. We can use the ruler postulate on both PQ and NM. However, for PN and for QM, we're stuck with the distance formula. Let's get our ordered pairs now, starting with M. M is at 5, 1. Then going down to, we're going left to N, we have negative 1, 1, and then down to P, we have negative 2, negative 5, and finally Q is at 4, negative 5. Okay, let's start with MN. So MN, since it's horizontal, we can use the ruler postulate and simply count the spaces in between each grid line. So we start with M and we work our way toward n. So it'd be 1, 2, 3, 4, 5, 6. So there's 6. Mn is 6. Then we go over to NP. And NP, we're going to have to use the distance formula. So we have the square root of. Using n and p, this one and this one, I'm going to let p be my second point. So this would be y2 and x2. Starting with x2, we have -2 minus -1 under the square root squared plus, and back over here to y2, -5 minus 1, quantity squared. So NP is equal to the square root of -2 minus -1 is -2 plus 1, which is -1 squared, plus -5 minus 1 is -6 squared. Then -1 squared is +1 plus -6 squared is 36. So we get NP is the square root of 37. Now, if you put that in your calculator, you'll notice the square root of 37 is slightly more than 6.1 I believe, which is not equal to Mn. So already we can see that this is not going to be a rhombus according to its definition. However, when you use coordinate geometry, you need to mathematically communicate that all four sides either are or are not a certain length, whatever you're trying to test. So we go on. Using PQ, we also have a horizontal line segment, so we start with P, ending over at Q, count the spaces, 1, 2, 3, 4, 5, 6. It's also 6, just like Mn. Then we move back over to our last segment, QM, or last side, MQ or QM. And we must use the distance formula here too, because this is not vertical or horizontal. So we have the square root of. This time we're using M and Q. And I'm going to let M be my second point this time. This is x2 and y2. Using the distance formula, x2, starting with x2, we have 5 minus 4, quantity squared, plus, and back over here to y2, we have 1 minus -5, squared, all under the square root. So QM is equal to 5 minus 4 is 1 squared, plus 1 minus -5 is 1 plus 5, which is 6 squared. That gives us the square root of 1 squared is 1, plus 6 squared is 36. And QM's length is the square root of 37, which is approximately about 6.1 again. So here, 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 and here show us that this is not going to be a rhombus. So since Mn is equal to PQ and MQ is equal to Pn, what is this? It's not a rhombus, but opposite sides are congruent to each other. That would make it a parallelogram. But just a general parallelogram. And then we need to state why it's not a rhombus. So, however, since Mn doesn't equal Pn, or MQ and PQ doesn't equal Pn or MQ, we determine that MNPQ is not a rhombus.